everybody. Back for some more linear algebra. Today I'll be reading, and I'm going to turn my volume up a little bit. Testing, testing, right? Today I'll be reading from chapter 6, section 4, the spectral theorem, as it says in the title, spectral theorem, as well as it'll talk about quadratic uh, formulations of matrices, is my understanding. So we'll go ahead and get that started. And I'm nearing the end of the class. So thankfully, actually, so I'll be able to spend more of my time on quantum mechanics after I'm through with this. So that should be good. So everything should be sharing okay. And I'll do mostly pad today. So we're in 6-4. Spectral theorem. So it says we now turn to the study of a large class of diagonalizable matrices. And to remind ourselves of the formula for diagonalizing a matrix, basically A equals P diagonalized P inverse. Therefore, P inverse diagonalized A P equals diagonalized matrix. So it's a process. Oh, and P are the eigenvectors of the set. We'll call this 1, 2. And I'll even call it E eigenvector. So that's how we get P, and that's how we get the diagonalized matrix. The symmetric matrices. Recall that a square matrix, A is symmetric when A equals AT. So symmetric A equals AT for a square matrix. And we'll call A equals A, B, C, D, whose characteristic polynomial is T equals T squared minus A plus C T minus A C minus B squared. I don't actually remember what the characteristic polynomial is. Let me refresh myself. This is from the first section in this chapter. A be a square matrix. The characteristic polynomial is PAT, which is det. Yeah, that's right. Det A minus TI is called the characteristic polynomial. That's right. So I don't know why so I guess this is a unique form of the characteristic polynomial. So default characteristic polynomial is P equals P A C, A being the matrix, equals the determinant, the matrix minus the identity matrix, or should I say to keep it in the same form, T, identity matrix, All right. On the other hand, the complex perspective. All right. So the characteristic polynomial is the polynomial we get when we solve this for a polynomial. All right. But the one that we're looking for has a unique form of this. But a quadratic formula is the eigenvalues are, to remind ourselves of the quadratic formula. Now remember, right, x equals negative b plus minus square root of b squared minus 4ac over 2a. So in that case, it equals negative a plus c. I guess I should say plus a plus c since it's already negative, plus minus the square root of a plus c squared minus 4, 1 ac minus b squared all over 2, 1. So let's see if this comes out to be the same. So we do have the plus a plus c plus or minus square root. Since the a plus c is negative and we're squaring it, the negative goes away. So it's just a plus c squared minus 4 ac minus b squared over 2. I'll draw this 2 better. So that could be simplified. Right? So that becomes right, a plus c plus or minus square root of a squared plus 2ac plus c squared minus 4ac plus 4b squared over 2a. So that becomes a plus c plus minus square root a squared. And we're going to go plus 4b squared plus c squared minus 2ac over 2a. Right? So it looks like they just, let's see. Then this becomes a plus c plus minus square root. And I group some things, a squared minus 2ac plus c squared plus 4b squared over 2a. So that becomes a plus c plus minus square root of, so this is a minus c squared plus 4b squared all over 2a. And that equals, we could say lambda. This is for the eigenvalue. since we're solving for what the t is, right? So we have the first thing we notice here is that both the eigenvalues are real. Okay, well, because whatever this is squared, so that's going to be positive. This is squared, so that's going to be positive. Yes, that's going to be real. Okay. When A is not diagonal to begin with, B equals not zero. And so the eigenvalues of A are necessarily distinct. Thus, in all instances, the symmetric matrix A is diagonalizable. However, the corresponding eigenvectors are and V2 equals lambda 2 minus CV. So apparently this is just simplifying this so that those are two eigenvalues and plugging it back into the matrix and solving for V, we get these two. And note that V dot V equals B squared minus C, or lambda squared minus C, plus B lambda 1 minus A, that's lambda 2. So that equals B lambda 2 plus lambda 1 minus A minus C equals 0, right? So eigenvectors are orthogonal. So I have to see that it always works. So there's an orthogonal basis for R2 consisting of eigenvectors, A. We of course have an orthonormal basis for R2 consisting of eigenvectors of A. That is, by an appropriate rotation of the usual basis, we obtain a diagonalizing basis for A. All right, well, let's look at this example and see what they're talking about. So we have A equals 1, 2, 2, negative 2. So let's find the eigenvalues and eigenvectors of the matrix. So we have the characteristic equation will be the determinant of A minus I lambda equals 0 because um, if we have right, and if we were to take uh, this matrix and multiply both sides by a value. I'm going to say ax lambda equals minus b lambda equals 0. And we can factor out the lambda. And actually, we back up. We have ax equals lambda x. That's what the proper one is. So identity times this side is the same, but identity times the other side makes this into a matrix. And now we can subtract that from both sides. And now we can factor that. So this means that x is in the null space of a minus I lambda. And the property of matrices is that the only way that this equation could equal 0 in this way is if the determinant of a minus lambda I equals 0, which means it's singular. So if that of that is singular, then we have a solution that's not just 0. So now we're over here trying to find out what that solution is. So we have that of 1, 2, 2, negative 2 minus lambda 0, 0, lambda, which equals determinant of 1 minus lambda 2, 2, lambda minus 2, or negative lambda minus 2 equals 0. So we have 1 minus lambda, negative lambda minus 2, minus 4 equals 0. So negative lambda minus 2 plus lambda squared plus 2 lambda minus 4 equals 0. So lambda squared plus lambda minus 6 equals 0. So we have lambda plus 3, lambda minus 2 equals 0. So lambda equals negative 3 and lambda equals 2. So to find out what the vectors are that fits this, we have so if lambda equals negative 3, we have 4, 2, 2, 1, 0, 0, which leads to row 2 minus row 1 divided by 2 is row 2. So we have 4, 2, 2 minus 2 is 0, 1 minus 1 is 0, 0, 0, linearly dependent as it should be. So then we have row 1 divided by 2 is row 1. So then we have actually divided by 4. So then we have 1, 1 half, 0, 0, 0, 0. So V1 equals 1 half V2. So V equals 1 half 1 V2. So V2 equals 2. So V equals 1, 2. That's 1 eigenvector. Let me make sure I did this properly. Okay, this is negative. The first thing. Would be negative. This would be negative, right? So lambda equals 2. We have, that's 2. We have negative 1, 2, 2, negative 4, 0, 0. So we have row 1 times 2 plus row 2, row 2. So we have negative 1, 2, 0, 0, 0, 0. Then we have V1 equals 2V2. So V equals 2, 1, V2. So letting V2 equal 1, V1 equals 2, 1, right? So we have lambda 1 equals 2, and V1 equals 2, 1. Lambda 2 equals negative 3. V2 equals negative 1, 2. So let's see what the problem wants us to do now. By making these vectors unit vectors, we obtain an orthonormal basis. All right, so let's see this. So we have V1 dot V2 that equals negative 2 plus 2 that equals 0. So we know they're orthogonal. So the magnitude of either equals square root of 2 squared plus 1 squared equals square root of 5. So unit vector V1 u equals 1 over square root of 5 2 1, and V2 unit vector equals 1 over square root of 5 negative 1 2. So the orthogonal is orthonormal, right? In general, we have the following important result. Its name comes from the word spectrum, which is associated with the physical concept of decomposing light into its component colors, which is a favorite of mine, by the way. I love Spectra. Theorem 4.1, spectral theorem. So this may be interesting. It has to do with something we do with spectra. A is a n by n matrix, symmetric. One, where lambda are real, so the eigenvalues are real. And we have two, there's an orthonormal basis. Q1 all the way to Qn. Earlier we found basically Q1 and Q2 for Rn, consisting of eigenvectors of A. Composed of Vi. That is, there is an orthonormal matrix Q, so that Q inverse AQ equals A is diagonal. So there we go with the diagonal definition. A equals Q diagonal Q inverse. So Q inverse A Q equals a diagonalized matrix. All right. Before we get to the proof, we recall the salient feature of symmetric matrices. From proposition 5.2 of chapter 2, recall that for all x, y, and Rn, and in matrices A, we have A x dot y equals x dot A p y. So we have a dot product moving the matrix. If the matrix is on the left component, the transpose moves it, and I suppose that should go both ways, the transpose. In particular, when A is symmetric. So that means that Ax dot y equals x dot ay when A is symmetric. So non-symmetric, you have to take the transpose. Symmetric, well, the transpose is the same thing, so it's the same thing. and they do a proof. We begin by proving that the eigenvalues of a symmetric matrix must be real. The proof begins with a trick to turn complex entities into real. Let lambda equals a plus bi be a potentially complex eigenvalue of a. I consider the real matrix. So they basically, right, so this is starting to seem like some uh, uh, quantum mechanics stuff. So that seems like a good time to take a break. We'll be going for about 30 minutes. So I'll take a break and I'll come back and start here by proving the actual spectral theorem, right? So we'll come back later with part 2.